Now, we already talked in energetics when we only looked at activation energy and enthalpy, and we sort of came up with some numbers that generally 100 maybe, less than 100, is considered small, kilojoules per mole for enthalpy and activation energy that leads to equilibrium reactions. Now that we've done this Gibbs, and we realize that we can also take away some entropy from the system as well. We come up with some ballpark figures that it gets a bit smaller than for Gibbs, so it's like plus or minus 30. So if it's about plus or minus 30 Gibbs free energy, then generally that could be an equilibrium. And so if the K equals to 1, it is equilibrium and there's no movement. If the K is greater than 1, we've already talked about the fact that is products over reactants, and that's too high. Greater than 1. So K is products over reactants. Reactants go to products. So this one's larger. And so it's generally going to go to that side. And delta H negative is favorable, delta S positive is favorable, and delta G negative is favorable. So it's favorable, so it's negative. The reverse is also true. So if K is greater than 1, then less than 1, then products must be smaller than they should be, reactants larger than they should be, and then so that's smaller, that's larger, and so it's favored more on the reactant side, and so it's not favored to actually go in that direction. So G is positive, and positive is not favorable for and according to that table there of that list there of what is the favorable signs, okay? And so we've talked about this before as well. So there's equilibrium is because there's a balance between entropy and enthalpy, and we've just gone into some ballpark figures of what they are. So completely on this, in this direction, it gives this delta G here, and in this direction, it's 0 delta. It goes to maximum of 0 delta G because they're in their natural states and they're happy to be that way. And somewhere in between it's minus 33 as delta G, which is very favorable. So they don't want to all be on one side or the other. They kind of like to be halfway in between. Okay, so this is more sort of the physics again. So there's a couple of equations, delta G equations in your data booklet. This is one of them. So when we get to this sort of physics stuff, these derived equations, the important thing is to know what they all are. So gas constant we've done before, temperature in Kelvin, K we've done, delta G we've done, and we haven't done this a heap, but we have done it. So E and Ln are natural logs, log to base E, not log to base 10. Okay, so you just need to know what they stand for, what they are, and I would just deal with questions as they come. See what variables you have, see what equations you can sub that into, and see if that gives you what the question is asking. And that's so I take a very physics approach to basically the physics now. Okay, so we're sort of, chemistry is applied physics, and now once we do high-level chemistry, I think we're just doing plain physics. So does chemistry exist? I don't know. So determine K, and you're given a delta H and a delta S and temperature. And so that you got to look up in your data booklet what you can actually do. You're trying to work out the K for this equation. You can't use Rice or a K expression because you've got none of the concentrations. You can get a delta G. All right, so formula substitute units, because you do have all of those, the delta H, the delta S, and the T. So in some senses, maybe you've done Suvac equations in year 10 physics or 9 physics. You sort of just work out the ones you can, and usually it's only 2 equations you have to use. That will get you the remaining ones to get to an equation that has K in it. So that's just natural log, that's fine. We're trying to work out K. We already have the gas constant because we always have it. It's in the data booklet. We just worked that one out, and we already had the T. Okay, so formula substitute, then you've got natural log of K equals that. So you have to convert between natural logs. which we'll touch with acids and bases a little more as well, which will help. And so that's your final result. Okay, so that's the approach I take. I just see what equations I have, see what I need, put the variables in, formula substitute units, and then I'll get the answer. Okay, getting to the point where a lot of derived equations get very physics. Okay, and the reaction obviously is really large, it's really favourable, and surprise, surprise, iron likes to rust. So try and do a large range of questions so you get used to that technique.